The send more money problem is a puzzle where you have to decide for every letter of the puzzle a value between 0 and 9 so that the addition holds. The way we will model this problem is by introducing what we call carry variable for representing the sum. Okay, it's really like you did when you were a child or you made additions because you may have a carry. For instance, if you have 9 plus 4, 9 plus 4 it means 13, and so you will have 3 here and the carry will be 1, okay, for the 13 to represent the 13 here, and so on. Okay, so this is really a traditional addition as you did when you were a child. And we will introduce one carry here, 4 different carry numbers, carry variables, and one variable for every type of letter. Okay, and in your model, these will be the decision variables. What are the constraints? The constraint will be that one. You will say first that the last carry, yes, you will say that you do not want to start here with a 0. Okay, so S must take the different value for 0. Every different letter, so every letter I and J, so that J is different from I, you say that they should take different values. It is just to avoid a situation where, for instance, S is equal to 4 and R is equal to 4 as well. You want to prevent this. And so this will be enforced by these constraints. For the carry, then you have the addition rules. You will say, let's consider the carry 4. The carry 4 must be immediately equal to the value, the variable m, of course. And then you have the addition rules. So you say the carry 3 plus the carry 3 plus the value of s plus the value of m. Okay, you take the plus, all of this is equal to the value of O plus 10 times the carry 4. Okay, and so this is really the traditional addition rules that you enforce here, by where you will link the carry with the previous additions. Okay, you enforce all these rules. Then you press the run button and you should discover a solution for the send more money with your best favorite constraint programming solver. What I want to explain to you now is a little bit the kind of reasoning that is performed for this problem using the fixed point computation that is used by the solvers. Let's consider the search space initially. So initially, the carry variables can take the value 0 or 1. Okay, so this is represented here. And about the other variables, so the variables for the send more money, they can take the values between 0 and 9. So initially, you may think, okay, I can deduce nothing. But this is not true. Because what the solver will do is already use this. The value of S and the value of M must be different from 0. So you already put in red the color here in the values corresponding to value 0 for the domain of variable S. And you also put in red the color for the variable M, okay, to say that S and M must take values different from 0. Okay. And since the carry 4 is equal to the value of m, the carry 4 is this one, it means that this can also not be a valid value for this variable, and so you will put it in red as well. Okay, now since this cannot be the one, it means that we now already have deduced that C4 must be equal to 1. The carry 4 must be equal to 1 in this case. Okay, if you remember in the send more money, the carry 4 was the one to the left, completely to the left. Okay, this was this one, carry 4. Okay, and so we know that the carry 4 is equal to 1. Okay, what can we deduce from this, that the carry 4 is equal to 1? It means that m, we also know that it's now equal to 1 because the value of m is equal to the value of carry 4. Okay, and so we know that this one, m should be equal to 1 as well. And since this one is 1, of course, as a consequence, you will remove the other values from the domain of this variable. Okay. And if you remember, the all different constraint that was acting between all the variables, they must take different values. And since we have decided to take the value 1 by propagation for the variable m, we should remove this value 1 for every possible other variables. Okay? And this is enforced by this set of constraints. And then we have the addition constraints, what I call the addition rules constraints that will link send more money variables with the carry variables. And these will also act and prune a little bit the domains. I will consider one, and we will look together the kind of addition that is made here. It's this one. Okay, the value of m, you can already replace it by 1 because we have decided this. Okay, it's in blue, so it's decided. And then I will try to analyze the left member and the right member of this equality. And what to deduce, and I will try to deduce possible intervals of values. So on the left, we have carry 3 plus value s plus 1. And we know that the range of this one, if I look optimistically, it will be between 3 and between 11. How I can deduce this is because the 3 comes from the fact that at the minimum for carry 3, if I take carry 3, the minimum value is 0, you see? And it corresponds to that one. Then the minimum value for s, I look in s, is this one, is at least 2. So I put 2, and then 1 is decided. So I've got here the 1 which is here. And this is why at the lowest level, the minimum value of this interval on the left is equal to 3. You can have the same reasoning for the highest possible value, and it will come to 11. You do the same kind of reasoning on the right, and you have something between 10 and 19. And so you have the interval 3, 11, and 10, 19 that should be the same. And so what you will do is that you will take the intersection of these two intervals in order to remove no solution. You want to keep every possible feasible solution. Okay, you take the intersection. Okay, you take the intersection, and since if you take the intersection of these two intervals, you've got 10, 11. And so you will force the left-hand side and the right-hand side to be on the range 10, 11. And then you will back propagate this new information inside every possible domains. Let's do this. We know that it's 10, 11. So you take the left part, which is this one, and you say the left part is between 10 and 11. And we'll see if we can make further deductions here. And the answer is yes, you can do further deductions. I will erase everything. Okay. You will isolate everything by putting -1 to the left and to the right. So you've got -1 now. Carry 3 and carry n value s. Okay. You put carry 3 to the left and you will isolate value s and try to make deductions. What is the smallest possible value for value s? You've got here a minus, and since you have a minus, the lowest possible value should be found by taking the maximum of carry 3. And the maximum of carry 3 is 1, and so it's 10 minus 1 minus 1. And so the smallest possible value will be 8 here. On the other side, what is the highest possible value there? Okay, you want to be optimistic, and since you've got something that you want to remove, you will remove the lowest possible value because you want an upper bound on the domain of S. And so you will have 11 minus 1 minus 0 now. So 11 minus 1, 10, minus 0, it means it's still 10. And so the value of S should be between 8 and 10. This is what I will discover here. I propagate this inside the domain of S. S was here. And now I know that S should take a value between 8 and 10. And so I will remove all this. I already know that the value of S should be something between 8 and 9. Okay? And so this is a kind of deduction that you can do. I will not explain it further. You can look at it by yourself. Okay, in the slides, I can make more deduction, and you can see that even before starting the search, I already have pruned a lot my search space by just making some basic reasoning on the constraints of my problem for this model. Okay, and it's just to this was just to give you an idea, of how powerful the propagation is in terms of reasoning for problems. So just by letting the constraint reasoning one at a time, we can already prune a lot the search space for many types of problems. Okay, you can really take a look at this. And then at the end, what I give is really the implementation of this problem inside mini-CP, okay, which is here. If I move forward. Okay, it's not important that I understand everything in details in terms of propagation. It was just to give you a taste of what the kind of reasoning is done. And this is the model inside mini-CP. Again, we have an array of variables here. The array of variables contains the possible ranges, and then you've got all the arithmetic constraints here. You've got an all different constraint to say that every values of send more money should take different values. You've got the not equal constraint at the beginning for the variable s and m, and then you have the carry constraints and the arithmetic constraint. And then you have the search component, and you see that in this specific case, I'm not programming the search myself. I'm relying here on a default search, which is called the first fail search. And then I say solve. Solve will just initialize the solver and perform the search and discover a feasible solution by itself. Okay, so this was for the send more money problem.